Hey everyone, welcome to the lecture for 3.5. So we'll be going over transformation of functions, and we have two SLOs associated with this section. The first one being the ability to state that I can transform functions using vertical shifts, horizontal shifts, and reflections. I can express these transformations graphically, algebraically, and verbally. And the other SLO, I can determine if a given function is even or odd. I can make this determination algebraically and graphically. So we're going to begin with vertical and horizontal shifts. That's going to be our first task. Then we're going to move into reflections. Then we'll go into even or odd. So starting with vertical and horizontal shifts, let's tackle vertical shifts. They are the easiest ones. The reason I say that is because it's exactly what you think it is. You just add a constant onto the end. So like, for example, here we have the blue line is the graph of the cube root of x. And in order to vertically shift it up by 1, we just add 1. So adding 1, right? So I'm looking here at the orange. And of course, if we subtracted 1, we would be looking something like this, right? Where we would just go down 1. So this would be f of x minus 1. Nope, not that one. F of x minus 1. Right, so adding 1 will move it up, subtracting 1 will move it down. Now, you know, if I had subtracted a -1, you want to make sure to simplify that and kind of keep that constant k. Think of it as a positive number so that the addition or subtraction corresponds exactly with up or down. So the book does it like this. They're like, well, I'm just going to add k, period. If k is positive, it's going to be up. If k is negative, it will shift down. So that's the same thing, right? Because if k is negative, you're really just subtracting the absolute value of k. That's if you want to get super technical, super nerdy. Just remember, if you're adding something to it, up. If you're taking away something from it, down. All right, so next what we want to do is we want to, from a graph, we want to see how we can shift vertically. We kind of just did that, but let's do another example here. So to regulate temperature in a green building, airflow vents near the roof open and close throughout the day. And this graph, figure 3, shows the area of open vents, V, in square feet throughout the day, in hours after midnight T. During the summer, facilities manager decides to try to better regulate temperature by increasing the amount of open vents by 20 square feet throughout the day. So we want to graph this change directly over the existing blue graph. So if the y-axis represents the amount of open vents in square feet, then increasing this amount of open vents by 20 is just going to be a vertical shift. So really what I'm talking about is V tilde, right? I have to differentiate it from V, is V of T plus 20. So that just means that everywhere this graph is, I'm just going to move it up by 20. So that's just like point by point. I kind of make myself a little guide here. So I'm saying that all these arrows are the same length, at least in theory. Right, so basically I'm kind of just putting this graph on stilts. And I'm just going to connect my dots here. Right, so this would be raising it up by 20. And we can also do it from a table. So here we're given that f of x is 1 when x is 2, 3 when x is 4, 7 when x is 6, 11 when x is 8, right? So we don't have an explicit function for f, but we just have a few values associated to some x values here given in this table. And what we want to do is we want to compute g of x equal to f of x minus 3. So it just means that when I'm computing g of x, I'm just going to take whatever f of x was and subtract 3, right? So I'm just stealing the f of x value and I'm subtracting 3. So that's going to give me -2, 0, 4, and 8. All right, so next what we have is a ball being thrown from the ground. And we want to compare that to if we were instead throwing the ball from a rooftop. So we have this nice parabolic motion for the ball, and it's given by h of t. So that's h of t equals -4.9 t squared plus 30t. And we want to throw it from the rooftop. So that's just going to be a vertical shift. So what we're going to have for b of t, right? So b of t is the new function according to this problem. It's going to equal h of t plus 10. But in this case, we actually have an explicit formula for h of t. So I can write it as -4.9 t squared plus 30t plus 10. So far what we've done for our vertical shifts, I'm going to sum it up under horizontal just to kind of keep a tab of what all we've done as we move forward. So if we're considering k to be positive, we're going to go up by k if we have something like f of x plus k. And then we're going to go down by k if we have something like f of x minus k. So now we need to look at the horizontal shift. So a horizontal shift happens, for x. Like for the vertical shift, we were just moving the y values. So f of x, our output, our range, that's y. That's height. So that's why we're just adding or subtracting k from it. For the horizontal shift, we have to think about x. That's the argument of the function. That's the input. So when I do a horizontal shift, I'm going to manipulate the argument of the function. And what I mean by that is, let's look here. Notice that we're adding to x before we have f act on it. So here we're changing x before applying f. So notice that this also represents a left shift. This went left by 1. This went left by 1. This went left by 1. And the takeaway here is that we're going to go left by h. And that's going to look like f of x plus h. So when I add to x, I'm actually going left. So this is a bit counterintuitive. If I want to go right by h, I'm going to subtract. And again, I'm thinking of h as a positive number. So they always, in the definition, they always say it's just f of x minus h. And then if h is positive, then we're going right. And if h is negative, we're going left. I say these are the same thing. I just describe them differently. So you can lean on whichever one works better for you. So here we want to look at what it means to start earlier. So if we want to start 2 hours earlier, the blue graph, again, V of t, it starts opening its vents at 8, which is 8 a.m., up until 19 when it finishes closing them, so 7 p.m. We want V tilde, the orange graph, we want it to be open from 6 to 17. So that's 2 hours earlier. So that's going to be a left shift. So everything's going to go left by 2. So I'm going to finish closing my vents here. I'll probably start closing them around this time. I'm going to open my vents at this time. So this is a left shift. So we know that if we want to shift V of t to the left, we're going to have to add 2. And then this is going to be our V tilde. So think about this, when I plug in 6, V tilde of 6, right, is when I start opening my vents. And that's the same time V of 6 plus 2, right? V of 8. That's when V starts opening its vents is at 8. So that's maybe justification here, hopefully, for the addition being the left shift. Right, so again, regular V is the blue line. So starting at 8 corresponds to starting at 6 for V tilde. All right, so we can also do this for a table. So here we have x and f of x, and we want to shift according to g of x equals f of x minus 3. So this is going to correspond with a right shift by 3. So what I want to do is g of x is going to equal f of x minus 3. So how do we figure out what our x has to be? So remember that g of x equals f of x minus 3. So in this particular case, so let's just look at one instance of this. Just looking at the first guy here. So when g of x equals 1, this has to still equal f of x minus 3. So then I come up here and I'm like, well, f of what equals 1? F of what equals 1? Well, I know that 1 equals f of 2, right? That's from the purple part. So this allows me to equate the arguments of f. So what this is telling me is that x minus 3 has to equal 2. And similarly for the next one, if I have, let's say, 3, right? If I'm going down the line, if I have 3, I know that has to equal f of x minus 3 just in general. But going up to the upper table, I know that 3 equals f of 4. So here I get that x minus 3 equals 4. So we're kind of establishing a pattern here. Notice that I'm going to add, in order to solve for x, I'm going to add 3. So here I get that x equals 5, and then the next one I get that x equals 7. And so I'm on my way. I don't need to do the other two because I know now that I'm just adding 3 to x. And I 100% understand and sympathize that the horizontal shift feels opposite of what is true, right? You think, okay, if I'm doing x minus 3, why don't I just subtract 3 from these values? Well, the argument is here when we take g of x and f of x and compare what their arguments have to be. It's not that we're going to subtract 3 from 2, 4, 6, and 8. It's that x minus 3 has to equal 2, 4, 6, and 8. And that's a big difference. So next we want to, from a toolkit function, we want to be able to transform a horizontal shift. Sorry, we want to be able to identify a horizontal shift. So this parabola, typically a parabola will just sit at the origin. Like if we're just doing our toolkit function, right, this would be our original guy, right? So this is f of x equals x squared. And so we're interested to know what g of x is. So g of x equals some transformation of f of x. And okay, so we know it's transformed. How is it transformed? Well, it appears that it's shifted to the right by 2. Right? So g of x equals f of x shifted right by 2. And the way that I do that is I just say it's equal to f of x minus 2. So again, remember that f of x minus h, f of x plus h, again, we're assuming that h is greater than 0. This is going to be a right shift. And this is going to be a left shift. So if I want to move my graph right, I've got to subtract off. Because think about this, I want this x minus 2, I want 2 to be related back to 0. So when x is 2, I have to subtract 2 from it for it to be 0. All right, so now we're going to put horizontal and vertical shifts together. So we are given the absolute value function, a toolkit function, and we are told to make h of x equal to f of x plus 1 minus 3. So let's just parse it out really quick. So in general, we have two things happening. We've got a horizontal shift and we have a vertical shift. So the vertical shift, it's going down by 3, and then it has a horizontal. And this is going, you might think it's going right because we're adding, but remember it's kind of opposite. So it's going left by 1. So we know what f of x is. F of x is the absolute value function. So if I have my absolute value function here, so I want to take this and the first thing I'm going to do is I'm going to move it down by 3. So I'm going to do this in 2 steps. I'm going to move it down by 3. So that means every point is going to come down 3. So I'll go down here. This will go down to here. This will go down. I'm just moving everything down 3 steps. So this is going to go down here. This will go down to here. And then this will go down to here. Okay, so now my new function, just for the vertical shift, just for down 3, is this. And then I'm going to go ahead and go left by 1. So now I'm going to move all of these orange dots over by 1. So I'm here, then I'm here, then I'm over here, I'm over here, over here, here, here. Right, so now I'm and so this green graph is my final. This is h of x. And remember, it was f of x plus 1 minus 3. So I'm going to have so f takes the absolute value of whatever. So my argument is x plus 1. So I'm going to take the absolute value of x plus 1. And then from that, I'm going to subtract 3. So that's what I get here. So now let's see if we can identify a combined horizontal and vertical shift. So this function here, our original guy would have been the square root function. Right, so f of x, the original, is just the square root of x. And I want to know, how did I get from f of x to that floating blue thing? So you could look at it 2 ways. You could say, actually, I'm just going to say the one way. Look at where it started. Let's compare kind of starting point to starting point. Or you could even look really at any point. So if you have the point 2, right? These are all of our corresponding points here, and we have another pair of corresponding points So for any of these points, you could just see, how did I get from one green to the other? So this one was up 1 over 2. So we went up 1 over 2. Let's make sure that's true on blue as well. I went, sorry, up 2 and over 1. So same as green, up 2 over 1. And then let's check on purple really quick, just to see. Up 2 and over 1. So we know that this transformation is up 2 over 1 is what we were saying, but this is really plus 2 vertical, right? And then right by 1. So if you have a vertical shift, that's going to be on the outside of f of x. If you have a horizontal shift and you're going to the right, that's going to be subtracting 1 away. So let's call, right, blue is h of x. So we know that h of x is f of x minus 1, right? That's our right by 1. That goes here. And then to that, I'm going to add 2. And that represents our vertical shift here. So I also know that f of x is the square root of x. So what I get is that h of x equals the square root of x minus 1 plus 2. So in the next video, we're going to talk about graphing functions using reflections about the axis, and I will see you shortly for that.